In the preceding chapters, we've looked at everything we need to know to get a focused beam onto a sample in a scanning electron microscope. So now on that focused position, we generate a signal, we collect that signal, and we assign that signal to a pixel in the image. Then we move our focus beam to a next position to record the next pixel. So to understand signal formation in scanning electron microscopy and to know what that signal tells us about the sample, we need to look at the interaction of the electron beam with a material, the electron-matter interaction. And to do so, we will first zoom in to a microscopic level. So say we take a material like this light board, we would zoom in further and further and further, we ultimately arrive at the level of atoms. So I'm going to draw an atom here. So in the core, an electron has protons and neutrons arranged in the nucleus. And so that nucleus has a net positive charge and is very, very small. Around this nucleus, there's a cloud of electrons, and these electrons will screen the potential, the electric field of this nucleus. And so the further we move away from the nucleus, so say I move over this line here, which I indicate by a radial position r, is the distance from the nucleus, the potential here will decay further and further as the charge of the nucleus will be screened more and more by the surrounding electrons. Now this cloud of electrons in a very simplistic model can be understood with the orbital model. So in the orbital model, the electrons are circling the nucleus in fixed orbits. So here is the image with 3 orbitals, and then each orbital contains electrons. So each orbital contains 2 electrons. So I will just, for simplicity here, indicate 1 electron per orbital. So now if an electron comes in, so an energetic electron comes in, strikes the material, it will travel somewhere in the vicinity of the nucleus. Of course, it may be that it travels very far away from the nucleus, let's say here in the space where there's not really a nucleus or an electron near. And in this case, the electron will not feel the potential, the attractive force of the nucleus, it will not feel the repellent force of the electrons, it will just continue. So here we have our incoming primary electron, it will be transmitted, and if that also is the case for all the other atoms in the material we look at, we have a transmitted electron that exits the material at the lower phase compared to where the beam was coming in. So transmitted electrons can constitute a signal in electron microscopy. Of course, the incoming electron may also be on the other extreme, traveling very close to the nucleus. So it can come in here, feel the attractive force of the nucleus, be slightly bended, and actually, like a comet around the sun, be displaced, deflected to go entirely back. So here we have the electron coming in, and then the electron comes out of the material here, and this is what we call a back scattered electron. So back as it travels back into the direction of the primary electron beam. And backscattered electrons, we'll see, also constitute a type of signal in an electron microscope. Of course, the deflection is dependent on the distance to the nucleus and the strength of the attraction here and the energy of the incoming electron. So it may also be that the electron is deflected, say, in this direction, in which case we have a forward scattered electron. So the electron is now scattered in the forward direction. It may exit the material, but it may also continue its path on into the material and then interact with other atoms in the material. Now, another case is when the electron travels a bit further away from the nucleus but so far away that it does not directly interact with the nucleus, but it interacts with one of the electrons in the orbital. So say we look at an electron coming in here, and then it undergoes an interaction with the electron in this orbital circling the nucleus. And so in this case, this electron here will feel the repelling force of the incoming electron and may actually be kicked out of the material, of its orbit, and the incoming electron may just continue its path, but with slightly less energy. So this is what we call an inelastically scattered electron. And so I draw it in purple, as it's still the incoming primary electron that goes on. It just has lost a little bit of energy in the interaction with this electron here, and that little bit of energy lost is used to exit this electron from its orbital and escape this atom. Now, if this electron travels and it gets out of the material, this is what we call a secondary electron. So a secondary electron is an electron that originates from an orbital somewhere in the material, has been kicked out by an incoming primary electron, and is then freed, travels into the material, and may at some point escape into vacuum. So these secondary electrons are also a type of signal we can detect. Now, if this happens, then of course this electron here is gone, and it leaves a hole in this orbital. So we have an orbital here that is not occupied, and then what can happen is that one of the electrons in another orbital, so say we have the electron in this orbital traveling around, may lose a bit of energy by falling from the higher level into this level closer to the nucleus. Now, if this happens, a little bit of energy is lost, and that loss of energy can lead to the emission of radiation. So, for instance, depending on the energy distance, the energy change between the levels, it can be an X-ray photon, but also if it's a little bit, it might also be a visible photon. But in most cases, it's X-rays. And as these X-rays are characteristic for the energy separation between these two orbitals, they're also characteristic for the type of atoms we have in the material. So these X-rays may also constitute a form of signal in scanning electron microscopy, also in transmission electron microscopy, that actually may tell us something about the atomic composition of the material. Now let's look at what that means. Well, so we have signals are composed of photons, so light signals, X-rays or visible photons that we can detect. But the other ones, the backscattered electrons and the secondary electrons, are actually electrons. So we have electrons coming in, we have electrons coming out of the material. Now, if outside the material we put a detector and we detect all the electrons that escape from our material, we can plot these electrons as a function of the energy with which they hit the detector. So I draw that here. And so one axis here is the energy axis, so energy E, and then here I plot the number of electrons n with a specific energy as they exit the material. So now this curve will typically look something like this. So we have an incoming electron energy, say we call this E0, so E0 is the energy of the electrons that are here coming in to the material. And so say this energy here is E0. Then of course the highest energy of the electrons that exit the material is actually E0. So we have some electrons at energy E0 that are actually exiting from the material. These are the backscattered electrons. Now they may also, if they are already scattered once, may also have lost a little bit of energy. So this is a peak here that is a little bit broad, And then basically we have some other loss mechanisms that may occur here, but we will ignore those as they don't lead to signals in electron microscopy. Basically, this is a curve that looks like this, and then at very low energies, we have another peak here, very high peak, which only goes to 0 at 0. So now the two different signals we have, and we can discriminate here. So these are very low energy electrons. This is the range where we have the secondary electrons, which we'll abbreviate with SE. So there's these electrons here are the SEs. And then here we have a wide range of energies, which are all what we call the backscattered electrons, or the BSEs. So those are the ones we had here, the incoming ones that are deflected and scattered back up. So in this distribution ends here at E0. Now note that this BSA range is very broad. It's a very high range in energies, but of course the majority is very close to E0. Now the SE range is typically in between 0 and 50 eV. And the further range, 50 eV up to E0, is the range for the backscattered electrons. And actually in this regime, most of the secondary electrons will have an energy in between 0 and 20 eV, or maybe even 10 eV. So these are really, really low energy electrons that that are exiting from the material. Now, to picture a full picture, there's also typically some discrete peaks here, which are assigned to what we call Auger electrons, and there may be some peaks here due to plasmon loss. But as I said, typically we don't use them in biological electron microscopy, so we may forget and we not go into the details of how these peaks originate. And we will focus on SEs, BSEs, and X-rays. Now, typically in an SEM, the energy E0 that we have, so the primary beam energy, E0, is in between 0 to 30 kilo electron volt if we look at scanning electron microscopy, while in transmission electron microscopy, E0 is in between typically 80 to 300 kilo electron volt. So this is the realm of transmission electron microscopy, or TEM. Note that recently there's quite some research going on into low energy TEM, which is the 80 kV, but actually people are also trying to push this lower and lower. The important thing is to note 0 to 30 kilo electron volt, low energy regime is SEM, 80 to 300 kV is TEM. And so this determines this value of the E0 here. So for SEM, this is maximum 30 kV with backscattered electrons exiting the material at 30 kilo electron volt, while in TEM, backscattered or forward scattered electrons may still have an energy of around 300 kV.